and welcome to the second of the talks I've been asked to give about the connection between ideas about the nature of light and the development of theories in physics, theories about the physical nature of the physical world. Today I'd like to talk about the work of Euclid, the geometer who worked in Alexandria in Egypt around about 300 BC. He was responsible for a definition which lasted for 2,200 years, essentially until 1919, and for a methodology, how to construct a theory, which is still influential today. But first, let's talk about camels. It may not be entirely obvious how camels connect with ideas about the nature of light, but I hope to show you that there is a logical argument that leads from camels to ideas about light, and indeed ultimately onto ideas about the modern computer. Whether I'll be able to persuade you of that remains to be seen. Camels were domesticated around about 1000 BC, 3000 years ago, and they transformed the world. For the first time it was possible to conduct large-scale, long-distance overland trade. Camels could take large quantities of goods across deserts, across mountains, so for the first time the Middle East had access to the perfumes of Arabia, the spices and treasures of India, the silks of Egypt. They could all be brought from these distant places to the Mediterranean coast and then taken by seaborne traders like the Phoenicians all the way around the Mediterranean, out into the Atlantic seaboard, even as far as Britain. The rise of large-scale international trade also promoted the rise of the great military empires designed to protect that trade, to control it and to exploit it. First you had the Assyrian Empire, then the Neo-Babylonian Empire, the Persian Empire, you see getting bigger and bigger. Eventually that was defeated by Alexander. Alexander's empire, when stretched from Greece through to northern India, eventually broke up into a series of Greek Hellenistic empires. In many ways what the camel produced was the first globalization. It has been described as this. You have trade that extends over the whole of the Eurasian landmass, and that produces increased contact between different races, ethnic groups, different religions, different people speaking different languages, having different ways of thinking. The world becomes much more cosmopolitan. You have trade between people of different races and languages and different ideas. You have empires which are so large they include peoples speaking different languages, having different religions, having different ideas. You have great trading cities where you can find people from all over the known world, mixing together, trading together. It's not surprising then that the middle of the 1st century BC is also a time when we get a revolution in ideas, in thinking. The German psychiatrist and philosopher Karl Jaspers has described this as the axial revolution. The middle of the 1st millennium BC is when we find the rise of thinkers whose names are still known to us, whose works have come down to us, and whose works are still discussed today and seen as relevant to the modern world. So in China you've got Confucius, Mencius, Lao Tzu, Chuang-Tzu, Mo-Tzu, Sun-Tzu, and many others. India, the rise of Buddha, scholars who study the Vedas and the Upanishads, the great literature of India. Zoroastrianism in Persia, you have the Hebrew prophets, Amos, Isaiah, and Jeremiah. In Greece you have the beginning of philosophy with Socrates, Plato, Aristotle, building on work that's been on earlier. The Asian coast. There have been many theories about why the world, the old world anyway, suddenly experiences this ferment of intellectual activity. My views about this are that it represents a transition from obsession with local questions, which have been important for people for most of human history, to thinkers who are concerned with universal questions. The Greek philosopher Diogenes was once challenged to say where he came from, and he came out with this phrase, "Cosmopolites, I am a citizen of the universe." And that reflects a way of thinking that is developing at this period. People are not thinking about their own city, their own culture. The great thinkers are thinking on a global scale. Most of human history we've lived in small groups, hunter-gatherers, as living in small agricultural villages. And so the important questions for people in small-scale society tend to be local questions. What does it mean? What do I have to do to be a good member of my family, my clan, my tribe, my village? What knowledge do I need to acquire to be able to earn a living in this particular place at this particular time under these particular local circumstances? Language is used as a way of communicating local culture, the stories of the people, their myths, where they came from, what their history is, the way of life. But in the middle of the first millennium BC, the great thinkers that arise across the world are asking universal questions. Is there anything that's true for all people in all places at all times? What does it mean not just to be a good Chinese or a good Greek, but a good human being? What does it mean to lead a good life generally? Do people have common views about this in different cultures and different places? What knowledge is true for all people in all places at all times? What knowledge is really constant everywhere? How do different languages relate to each other? Are they commensurable? Is it possible to say anything that you can say in one language in any other language? Or are they incommensurable? Can you say things in one language which are difficult to translate into another language? Maybe impossible. How do people communicate efficiently across cultures, across different languages? These are sort of questions that people are asking in the middle of the first millennium BC. Even sort of metaphors that people use change. In the ancient world, mountains were often used as a metaphor for the eternal, because the eternal was also local. So the mountains were the place where the ancestors lived, or the spirits of the people lived, the gods lived. They were eternal, but they were also local. From the middle of the first millennium, from China to Greece, heavens become a metaphor for ideas that are both universal and eternal. The heavens are the same everywhere for all people, and they've been the same from generation to generation. So this change from thinking locally to thinking universally, globally, I think, is something that happens in the middle of the first millennium BC. Particularly people are interested in communication. How can we communicate across culture? What's the nature of language? The most primitive form of communication is the mime, the facial expression, the gesture. Even the great apes can communicate using mimes and gestures. It's been estimated by scholars that great apes like the chimpanzees or the bonobos have hundreds of different gestures and facial expressions to communicate with. Infants communicate in the same way. And if we go on holiday to a culture where we don't speak the language, we're reduced to the same thing. If you're hungry, you have to mime eating, or if you're thirsty, you have to mime drinking to be able to communicate. But with the rise of spoken language, human beings acquired a very powerful and versatile tool. Language can be used in many ways. For example, it can be used to tell stories. All cultures have delighted in storytelling. Even young children love listening to stories, they love telling stories. There's a metaphorical, poetical use of language where it's not used in a literal sense, but people refer to things which are connected in their minds but are not connected literally. So we refer in the West to greedy people as pigs, We're not saying they're actually pigs, we're just, in Western culture, pigs are associated with greediness. And then there's the simple, basic, logical use of language. That's just using the literal meaning of words and their logical connections. All languages have words which indicate logical connections: on top of, below, next to, bigger than, smaller than. So there is that basic logical use of language. Now, mimes are universal. They exist even in, say, the great apes, and all cultures use mimes and gestures. Narratives tend to be specific to a particular culture. So when Confucius wants to make a point, for example, he often refers to individuals or events in ancient Chinese history. He expects that his students, the people who are listening to him, will already know those stories. But for people who don't know those stories, the points he's making can be quite hard to understand. Same in the Greeks used to refer to their myths in their discussions. In medieval Europe, scholars would refer to stories in the Bible to make points. Islamic scholars refer to the Quran and Hadith in making points in their discussions. So the fund of stories tends to be rather culture dependent. Similar sort of metaphors that people use depend on their way of life, sort of things which are part of their daily experience. So saying that someone had a heart of gold wouldn't mean anything in a culture that didn't have gold, or which didn't regard gold as particularly valuable. Similarly, referring to someone as a pig wouldn't have any meaning in a culture that had no pigs, or didn't associate pigs with greediness. So metaphors, poetry, tend to be culture dependent. But the logical use of language tends to be fairly universal. All languages tend to have the same set of logical connections, basic words that mean cover basic ideas and have a basic connection to each other. The first person to really study the logical use of language was Aristotle. His ideas about the logical use of language and how to construct valid rational arguments and how to detect when arguments are not valid. His writings on those influenced the ancient world, they influenced Islamic culture, they influenced medieval European culture. Aristotle starts from very simple logical arguments. The simplest he can think of, he calls the syllogism. It's just a 3-line argument. The syllogism starts with 2 statements that are assumed to be true, and then a conclusion is deduced from those. For example, the simplest one, the classic one, all men are mortal. Socrates is a man. If those 2 statements are true, then it must be the case that Socrates too is mortal. It must be the case because of the literal meaning of these words and their logical connections. We can explain their logical connections in a Venn diagram. The set of all living beings that die is very large. Human beings form a subset completely within that greater set. And Socrates is one individual within the subset of human beings. So if Socrates is within the subset of human beings, he inevitably is within the greater set of mortal creatures. This is a logical necessity. It's not possible for that conclusion to be false, given the meaning of the words and their logical connection. Euclid tried to apply this logical, deductive way of arguing to geometry. Geometry literally in Greek means earth measurement, and Herodotus, the Greek historian, says that it was developed in Egypt because in Egypt the Nile floods every year. This is why the Nile Valley is so fertile. The soil is renewed every year, nutrients brought down from higher up the Nile. But the consequence of the flooding is that the field boundaries are obliterated. And Herodotus says that every year the Egyptians had to measure out their fields again and re-establish the boundaries. And this made them very good at surveying, measurement, and dealing with mathematical shapes. What we now call geometry. Geometry now is just essentially the mathematics of shapes. Euclid's achievement, working at the Great Library at Alexandria, was to compile all the known geometrical knowledge of his time. But much more than that, he reduced it all to a single deductive system. This is the key element in Euclid's achievement. What he showed was that all the known geometrical knowledge of his time could be deduced through simple logical argument from a few basic principles. This is his method. He starts with first principles. He defines all the key technical terms he's going to use, things like point, line, straight line. They're given clear definitions. He states the assumptions he's going to make. There are only 5 of them, and some of them seem just completely obvious, like he assumes it's possible to draw a straight line between any 2 points. Who's going to argue with that? He also states common ideas that he's going to make use of in his arguments. Again, some of these seem things that nobody's going to argue with. He states, for example, that if 2 things are both equal to a third thing, then they must be equal to each other. So, expressing that mathematically, if A equals B and B equals C, then because A and C are both equal to B, then they must be equal to each other. Again, few people are going to argue with that, but he states that he's going to need to use those relationships in his arguments. Having stated these assumptions and defined the words, everything else is deduced by logical deduction. He goes step by step, deduction by deduction, through to final conclusions. And because of this method, the conclusions he reaches are absolutely certainly true. If and only if, this is the philosopher's if and only if, all the starting assumptions are true and all the steps in the logical deduction are valid. It's hard to see this here, but for example, one of the deductions he makes is Pythagoras' theorem, that if you have a triangle which contains a right angle, then the square on the longest side, the hypotenuse, will be equal to the sum of the squares on the other 2 sides. Now, this is not an obvious conclusion. I mean, you may have thought that the conclusion of the syllogism that Socrates is mortal was not particularly surprising. You'd be more impressed if I'd produced a logical proof that Socrates was immortal. But a logical proof that Pythagoras' theorem is true, that's quite an achievement. It's not obvious that it's true at all. And yet it is true by force of logic. It cannot be not true. It has to be true for every right-angled triangle that's ever been drawn, from the beginning of whenever people first drew the right-angled triangle to the end of time and in all places. It must be true for every right-angled triangle ever drawn throughout history. People were impressed by that. I'm impressed by that. However, you may be getting a little frustrated because I'm supposed to be talking about light, and you're saying this ancient history is all very interesting, but how does it connect with light? I've said that in his starting principles, Euclid had to define what he meant by his key words. So he takes a word like point and says, oh, well, that's something that's so small it has no points, essentially it has no size at all. It can have a position, you can locate a point, but it doesn't have any size. Now, notice, this doesn't exist in the real world. This is just an idea, a concept. Everything, if you make a mark on a piece of paper, it has to have some size. Everything in the real world has some size. So the idea of something that has a position but no size is not something that exists in the real world. It's a pure idea, it's a concept, it exists in the mind. Similarly, he says a line is something which connects 2 points. He sees the ends of the line as being points. And the line has a length, but it has no width and no depth. It just has a length. It's a one-dimensional object. Again, they don't exist in the real world. You draw a line on a piece of paper and the line will have some width and it also have some depth. But Euclid ignores that. Of course, we can treat real points and real lines as being like ideal points and ideal lines when, the size is not important or the width and the breadth is not important. But then we come to the key definition. What is meant by a straight line? This is very important for Euclid because most of the shapes he's going to deal with are constructed out of straight lines. The triangle, the square, hexagons, octagons, all these shapes are made out of straight lines. So it's important we know what a straight line is. What he says is a straight line is a line which lines evenly with the points on itself. At first sight that might seem a little bit obscure, but what it means, he's just taking the practical method that people use and did use in his time to check that things are straight. For example, if a Fletcher making an arrow wants to check that the arrow is straight, he looks along it, and if it's straight, all the points along the arrow will seem to coincide to a single point. All the points line up one after the other. Similarly, someone making a sword, say, if they want to check the edge is straight, they would look along it, and if it's straight, all the points on the edge will seem to line up one behind the other. Similarly, someone trying to check today that say that the guitar is straight, the neck hasn't become warped and bent, they'd look along it to make sure that everything lines up. In the ancient world, people were able to construct straight lines over miles and miles and miles. When the Romans built their roads, they constructed straight line roads which extend mile after mile after mile. And it's relatively easy to do it. You just have to put in posts, sighting posts, and make sure that they all line up. So that when you look along the line that you want, each post is lined up one behind the other. They appear to line up one behind the other because light that's been reflected from each post takes the same path into the eye of the observer. So all these things appear on a straight line. They all appear to line up because they lie on the same light path. Light reflected from each of them follows the same path into the eye. Therefore we see them lined up. So this is what's known as the line of sight definition. So a line is straight if and only if it coincides with the path followed by a ray of light. Notice, this is a definition. When I was a schoolboy, we were told by our physics teachers that light was shown experimentally to travel in straight lines. They lied to us. It's not true. Euclid defined a straight line as the path followed by light. Light follows straight line paths by definition. In 1915, when Einstein questioned that definition, the scientific world had problems. Let's just take a minute to appreciate what Euclid achieved. He starts off with 2 pages of definitions, states 5 assumptions, 5 common ideas, common sense ideas you might say, that he's going to use. And from this small beginning, 2 pages, he derives, simply by logical deduction, nearly 500 different items of information about shapes, geometrical propositions. They fill 13 books of conclusions. And people thought that was an amazing achievement. It impressed people for the next 2,000 years. It impressed Newton, it impressed Einstein when he first read Euclid's book. The demonstrations usually, traditionally, geometers end a proof with the word QED, quadratic demonstration, that which was to be demonstrated. And once something had been demonstrated logically, assuming that the logic was valid, then it was certainly true. The conclusion was certainly true. Plato used the Greek word episteme to mean this sort of absolutely certain, logically demonstrated knowledge. He was so impressed by geometry, it's said that he had written over the doorway by which he entered his school, the academy, "Let no one ignorant of geometry enter here." He considered that the truths derived in geometry were examples of his eternal forms, truths which were true in all places at all times forever. In Latin, the Greek word episteme is translated as scientia, and in the 17th and 18th century, the founders of modern science were really trying to imitate Euclid in developing theories about the world which would lead to conclusions as absolutely certain and universal as those Euclid had derived about shapes in geometry. Just a little bit of a warning before we go in. When we look at the physical sciences, we have to remain aware there is a difference between theory and the real world. So, in constructing a theory, scientists are generally doing the sort of thing that Euclid tried to do. They take ideas which don't necessarily exist in the real world, so things like point and line, as I said, they're ideas, they're concepts, they don't exist in the real world. They're created by the human mind, but they have logical relationships to each other, so you can develop elaborate structures simply by logical deduction from these simple starting points. In science, we start with observations. These are in the real world. We observe things using our senses, and then those are organised by the brain. We process observations, we categorise them, we classify them, we measure things, producing data. And then we try and abstract patterns from the data. Theory connects with the patterns we get from observations, in that theory enables us to construct maps which show the same patterns as patterns we see in the data. But the warning I want to give is to try and always be clear that a map is not the same thing as the reality it maps. This is a map of the London Underground. It shows symbolically the way the different stations in the London Underground connect together, so it enables people to plan a journey from one station to another. However, the map is not the same as the London Underground. This is a picture of the London Underground. So a theory enables us to map the world that we experience, or to map certain patterns in it, but the theory is not the same as the real thing. So later on I'm going to argue that when we talk about things like quantum wave functions or space-time continua, we should see these things as being theoretical ideas produced by the mind, not things which exist in the world of the senses. Some consequences of Euclid's achievement. Euclid achieves his certain results by focusing on simply the logical use of language. No stories, no metaphors, no poetry, just the simple literal use of language and the logical relationship between words in language. This makes it rather boring because people enjoy stories. They enjoy using elaborate metaphors. Even being young children, we enjoy these things. We rarely use language in a purely logical, literal sense. That's just boring. It's powerful. It enables us to think very clearly, and it enables us to communicate our ideas very clearly. But it's pretty boring. The logical extension of Euclid's method is to develop a language which doesn't have these capacities to tell stories or to construct elaborate metaphors, but simply has logical connections. And mathematics itself is essentially a language which is purely logical. You can't tell stories in mathematics. You can't write poetry in mathematics. Well, maybe mathematicians would disagree with me, but I don't think you can write poetry in mathematics, because the meaning of mathematical symbols is purely their logical relationship to other symbols. They don't relate to anything in our experience. The words of normal language have meaning derived from experience. We know what a tree is, we know what a dog is, because we've experienced these things. But we don't know what mathematical symbols mean. They only have a meaning because of their defined relationship to other symbols. So mathematics is pure logic, very powerful, but for many people quite boring. In the middle of the 20th century, Alan Turing made an interesting connection. He thought that mathematical proofs, using this method of logical deduction, go through a series of stages. Each deduction follows inevitably from the previous state of the argument. So an argument develops stage by stage by stage, inevitably. It reminded him of a machine. Machines go through stages, inevitably, where one stage follows on from another. This is the internal combustion engine. So air and fuel are taken into the cylinder, they're compressed, they're ignited, the exhaust gases are pushed out, the cycle starts again, more fuel and air is sucked in. These stages follow each other inevitably. Turing argued that it should be possible to build machines which can read logical instructions and convert them into machine operations. So you could build a machine that you could give logical instructions to. You could build a programmable machine that would do pretty well anything. This, of course, is the idea behind the modern computer. Finally, I'm sorry to extend this lecture rather needlessly, really, but there's a wonderful story told about Euclid, which I used to tell my students, and so I'm going to tell it to you. I once went to a high school in Himeji in western Japan, and written up in huge letters in the entrance foyer, in English, there was this expression: "There is no royal road." I was amazed to find this story was known in Japan, because we don't often tell it in England now. This is a story about Euclid. When Euclid started developing his new geometry, the pharaoh Ptolemy I ordered him to come to the palace and give a series of lectures about the new geometry. Euclid went to the palace, he lectured Ptolemy on the new geometry. At the end of the first lecture, Ptolemy said how much he'd enjoyed it, and he was looking forward to the second lecture, at which point Euclid started fishing in his bag and produced a piece of papyrus, I suppose it would be in Egypt, and handed this scrap of papyrus to a courtier, asked him to give it to the pharaoh. When the pharaoh looked at the papyrus, his mood changed. He suddenly became quite angry, because written on the papyrus was a set of exercises and a note asking the pharaoh to work through the exercises before the second lecture. The pharaoh was insulted. Pharaoh's not a schoolboy. Pharaoh is the king of Egypt. He has to govern the country. Pharaohs are busy people. Pharaohs don't have time to do homework. Euclid was very sad and said, "Well, in that case, Your Majesty, you will never master geometry. There is no royal road to geometry." This was a personal comment to Ptolemy, because Ptolemy had been a friend and companion of Alexander the Great. He'd been a general with Alexander when Alexander conquered the Persian Empire. So Ptolemy knew well enough that in the Persian Empire there was a magnificent royal road. It ran 1,677 miles across the Persian Empire, a smooth road which the king's messengers could ride along. Every 15 miles there were stations where they could get fresh horses. King's messengers could carry a message across the empire in a week, but the road could only be used for the king's business. So the common people they had to use the dirt tracks and the mountain paths, and the same journey would take them over 3 months. So there were literally 2 ways to cross the Persian Empire. There was the easy way, the royal road, and there was the hard way. And Euclid is saying to Ptolemy, but with geometry, there's no easy way. You do it the hard way, or you don't do it at all. And that's a useful message, I think, for all students. And I was glad to see it in Himeji. At the end of this long lecture, these are the things that I hope you'll remember. Euclid defined a straight line as the path followed by light. The straight line nature of light becomes a matter of definition. It's based on practical ways in which people check that edges are straight, but he incorporates it into his system as a definition. The system itself, this idea that you can deduce knowledge by purely deductive arguments, starting from a few simple principles, definitions, assumptions, common ideas, that becomes the basis of the way we try and construct modern scientific theories even today. Arguments based purely on deductive logic are universal in that everyone who understands the logic is forced to accept the conclusions if they understand them, and because they just draw on the logical use of language, they're pretty easily translatable from one language to another. The success of Euclid's geometry promoted the development of maths as a purely logical language, which you can make more and more elaborate logical deductions using the symbols of mathematics. And in the 20th century it led to the idea that logical instructions can be converted into machine operations and the development of modern computers. So all in all, we owe a lot to Euclid. Finally, an illustration of the way in which logical arguments can be easily translated. 1601, Matteo Ricci, the Jesuit missionary, arrived in China. He set about learning Chinese and eventually took on students. One of his students was Xu Guangji Qi, and together they managed to translate the first 8 books of Euclid's Elements, Euclid's book, into Chinese. It was maybe an obvious one to try to start with, because logical language is relatively easy to translate. Poetry is hard to translate, but maths and science are not. So this text could be easily appreciated by Chinese mathematicians. They understood the arguments that Euclid was making. They understood, many of them, the power of his method. And this is the power of the logical use of language. It may be boring, but it's universal. Anyone can understand it. Hence, mathematics and science form truly global communities. The arguments, the ideas that they produce can be understood by anyone. In many ways, that all begins with Euclid. Thank you.